So this seminar is generally chaired by Professor Drensky. However, he's also giving the talk today. So I'll do the chairing instead. So it's my pleasure to announce today's talk by Vesselin Drensky. The title is The Bulgarian Solitaire and Other Games on Partitions. Please, Professor Drensky.
I start with this, that there is a meta-theorem which states that with a probability close to 1, the theorems and the discoveries, they are not named after the person who did it, but somebody else. So here, Bulgarian Solitaire, this is not Bulgarian, this is Russian. But the Bulgarians are not guilty because the name was given by people from Sweden. So this is dedicated to Ualbai Umirbaev and Leonid Makar-Limanov. They are my friends. They are great mathematicians, remarkable persons. You see in the YY. In May 2020, the university in Nur-Sultan, they decided to organize a conference dedicated to the 60th anniversary of Ualbai and the 75th anniversary of Makar-Limanov. I was invited to give the talk. I prepared it. The organizers even wanted to buy my ticket, but the meeting was canceled because of the COVID pandemic. So now this present talk is based on the talk I wanted to give in Nur-Sultan. So, and I will be honest that starting from 2015, this is the 7th time I give a talk on the Bulgarian Solitaire. But every time I add something new and also take into account the level of the audience. And of course, you can ask why this time I choose the same topic for the present talk. And the answer is very simple, that Sergei, the son of Makar-Limanov, discovered the Bulgarian Solitaire when he was 12 years old. So this is a list of the talks which I have given the first time in 2015. This was in the spring conference of the Union of the Bulgarian Mathematicians. I was invited to give a talk, and it was the first time. There was in a conference in Sofia, in Belgium, in another conference in Bulgaria, in Bulgarian this time, also another conference in Bulgaria and also in Bucharest. So, and I start from the very end. So this story is very funny, and this is an example how an elementary mathematical game can inspire serious mathematical investigations in many branches, in combinatorics, graph theory, discrete dynamical system, cellular automata, linear algebra, statistics, economical models, etc., etc. And also it can be presented in a funny way to attract young people to research. Even there were some demonstrations in the kindergarten in America. So, and this is based on my paper, which is published in the proceedings of the spring conference of the Union of Bulgarian Mathematicians. This is also in archive. If in archive you choose Drensky and Bulgarian Solitaire, you can download the paper. But also there are many things which are added after the talk, after the paper. So, and you can make an experiment. You open mathematical reviews and you write Bulgarian in the title. You see that you have 4 publications. 12 of them are for the Bulgarian Solitaire, and the others Bulgarian mathematicians, Bulgarian meetings, dictionaries, etc., etc. And if you see the journals, you can see that there is a nice list of journals. Also, there are several papers which are in good journals, but Bulgarian is not in the title. So also, if you see the languages, you have papers, you have PhD thesis, Master of Science thesis, preprints, computer codes, secondary school students working on this, etc., etc. You see, you have Russian, Bulgarian, Swedish, English, French, German, Italian, Portuguese. Also, there is something in Chinese. And even there is a small movie in YouTube, which was inspired more or less from my paper. There are also some codes written in different languages, some lectures. Okay, this is from Sweden. This is not inspired by me. This is simply some other solitaire, etc., etc. And this is, you know that the word solitaire, this means a card game played by one person. You have a pack of cards, and you divide this in several decks. And each move is you remove one card from each deck, and you collect, and you form a new deck. And the game ends when the same position occurs twice. For example, if you have this situation 4-3-3, you have one pile of 4 cards, two piles of 3 cards. You take one card from each, you make a new pile here, and you have here, this is the situation. And of course, if you want to translate the problem in the language of mathematics, you can simply write the number of the cards in each pile. And you can arrange them in a non-increasing order. For example, starting from 4-3-3, you get 3-3-2-2. With red, you have the new pile. Then again, you have one pile of 4, the other 10. The next step, this with one day disappear, and you have etc., etc. It turns out that in this case, in several moves, you get the situation 4-3-2-1 cards in the piles, and this is already you repeat the same thing every time. And of course, if you go further, translate this in the language of mathematics, you can translate everything in the language of partitions. A partition, this is sequence of non-negative integers such that the sum is equal to n, and this is a partition of n. There is a standard notation, and if you denote by Pn the set of all partitions, so the partitions are classical objects. You know this famous letter from Goldbach to Euler, when Goldbach states his famous conjecture that every even integer greater than 2 is a sum of here. This is every integer greater than 2 is a sum of 3 primes. In that time, 1 was considered to be prime, so this is why this is stated. And if you ask in which language was written the letter was in German. Here, this is the conjecture is stated here. But this is the conjecture is also some mixture of German and Latin. It says it seems that each integer greater than 2 is a sum of 3 primes. So this is something which is this is strange that the conjecture is stated here in the margin of this one. And also, Goldbach discusses the problem for presenting positive integers as partitions in prime parts. You can see here, this is a piece of the letter when you have partitions. And if you translate this in the language of partitions, the Bulgarian Solitaire is the following. You have an operator from the set of the partitions of n to the set of partitions of n, which sends each partition, if LC, the last one is bigger than 0, to a partition of this form. And if C is smaller than some of these things, you move C in the correct place. And if starting from some partition, the game stops when you have 2 equals results applying the operators. And in the above example, for example, you have 4, 3, 3, 3, 3, 2, 2, etc., etc. And the 9th step and the 10th step, they are the same. You see, you have this one. Also, if you work with another integer, partition of 7, for example, you get also something. But and for me, how the thing started. In 2005, I got a message from a Henrik Eriksson, which stated that he was invited to write a paper about the Bulgarian Solitaire for monthly. And 25 years ago, Gerd Almqvist, his friend, visited our institute. And Henrik thinks that Alquist told him the problem, and then the problem went to the West, and the problem became really popular when Martin Gardner wrote a paper about the Bulgarian Solitaire in 1983. So Henrik asked me who taught Alquist the problem, me or one colleague of me, Angel Popov, and who taught us the problem. Is it the problem Russian? Because Gert Alquist thought that this is the case, and who gave the name Bulgarian Solitaire? Honestly speaking, Henrik Eriksson, he gave the name Bulgarian Solitaire. And I answered that there was a Russian visitor in our institute. He told the problem to us. And two of my colleagues, they found the solution. In that time, Gert was in Sofia. And I don't remember me or Angel Popov. Some of us told him the problem. And then after this, I connected Henrik with two of my colleagues, Boruslav Boyanov. And Boruslav Boyanov told him the story. The story is that the problem was brought to Bulgaria by Anatoly Karatsuba from the Stiklov Institute in Moscow. Of course, everyone knows who is Karatsuba. And he visited our institute in 1980. And after the lecture, the seminar on the approximation theory, he told his colleagues the story of the problem. Konstantin Skolkov, he was a professor in the Stiklov Institute. He traveled from Moscow to St. Petersburg in the night to give a talk there. And there was another person in the compartment, and they started the conversation. When the other person learned that Skolkov is a mathematician, he showed him the card game. And it turns out that if the integers is triangular, so the first of the sum of the first k numbers, then finally you reach this stable situation 132k. And it seems that I'm not sure about this, that the experiment was with 15 cards. When Skolkov returned to Moscow, he told the problem to the people of the Stiklov Institute. And Karatsuba described this in the following way. When Gennady Arkhipov learned about the problem, his face took a satanic expression. He ran to his office, closed the door, and didn't come out until he solved the problem. Boruslav Boyanov, he also decided, he also liked such problems. In that time, he had already three boys, and when the boys they went to bed, he started to think about the problem and found the solution. The next day, it turns out that one of another colleague, Penchu Petrushev, he also had a solution. And in that time, one of our colleagues was an editor in the Bulgarian High School Mathematical Journal, Education in Mathematics, and he published the problem as a non-original problem in the section competition problem in 1980. And there were no solutions. The next year, the solution, it was published, the original solution by Boruslav Boyanov. And in that time, the problem appeared in Quant. So it was published by Sergei Limanov and Andrei Tom, again in 1998 in the Russian Mathematical Journal. And I contacted them, and it turns out the following. Sergei Makar-Limanov, he was 12 years old in that time, of Leonid Makar-Limanov. Leonid Makar is now in the public. He asked his father what happens when we have several piles of cards and we take one card from each pile and we make a new. And Leonid Makar-Limanov thought, okay, we should ask Quant what happens. And in that time, okay, this is the son of Makar-Limanov, 3 years ago. He defended his PhD thesis, and now, as I know, he's in the computer business. And in that time, Andrei Tom, he wrote a book about mathematical Olympiads, and they discussed the problem with the authors. But, and also it seems that they made some experiments, and Tom found a geometric interpretation in the case of a triangular number, and in the same time, the problem appeared in the Russian journal Quant, and later it was included in a book about mathematical Olympiads by correspondence in Russian. And it also, this solution contains also some analysis in the general case, when the number of the card is not triangular but any. And it seems that both solutions, they are the first published solutions in the Bulgarian Solitaire, the solution of Bryanov and the solution of Tom. And now, when Gerd Almquist was in Bulgaria, he visited our department of algebra in that time. He learned the problem and told him to Henrik Eriksson. In that time, he was in the Royal Institute of Technology in Stockholm. And also Eriksson had some experience in the popularization of mathematics as a scriptwriter, as a speaker in the educational TV and radio. And he wrote a paper in Swedish, Bulgarian Solitaire. So I'm afraid I'm not sure I can pronounce this, Bulgarian Patience, or I don't know how. And he presented a solution and gave the name Bulgarian Solitaire. Then he visited the States and spread the puzzle there. Jürgen Brandt from Aarhus University in Denmark, he also learned about the problem, but without the name, and he published another solution. He also analyzed the general case. So in the paper starts with the problem to be discussed in the following has been circulating for some time. And Donald Knuth, he used this Bulgarian Solitaire to start his programming and problem-solving seminar in Stanford. And finally, with the help of Ron Graham, the problem reached Martin Gardner, who included this in his paper, Bulgarian Solitaire and other seemingly endless tasks in 1984. And it was the starting point of the popularity of the Bulgarian Solitaire among mathematicians all over the world, and the main source of references for many years. So already 35 years from that time. Okay, this 35 years was a little bit earlier, so they are more than 35 because from 1983. There are different generalizations. I speak a little bit about them later. So, but Henrik Eriksson, he never wrote the paper about the Bulgarian Solitaire, but 5 years later, the story appeared in another paper by Brian Hopkins, 30 years of Bulgarian Solitaire. And finally, the real story about the train, etc., reached the large audience. And in the first publications, the Bulgarian Solitaire appears in 3 different versions. In the Bulgarian versions, they are both grouped in piles. In the Russian version, a clerk from the Circumlocusum office rearranges piles of volumes of the Encyclopedia Britannica. You know that this office, this is a place of endless confusion in the Little Dorrit by Charles Dickens, and the Swedish text is with cards. So it's interesting that Donald Knuth advised his student, and you can't save money by using old punched cards that computer centers are throwing away, since the cards don't have to have any distinguished marks. So also it appeared in an Australian journal in the forum about some goats, herds of goats which moved every 5 minutes, etc., etc. And even in some meeting of teachers in spectrum mathematics, my colleagues, they demonstrated this with clementines. They offered for catering 10 cups of coffee, 15 cups of tea, and 5 sets of 10 clementines. And I saw also something, it was demonstrated in American kindergarten. Then King Kong wants to have fun in New York, and he removes the top floor from each skyscraper and then makes a new skyscraper out from these floors. So, for example, you have 2 skyscrapers, and you remove the top floors and you make one new skyscraper. So, of course, if you have partition, the partitions usually they are visualized by young diagrams, where the boxes are arranged to have the same beginning from the left side, and the corresponding part of the partition, this is the number of boxes of each row. For example, here you have 4, 3, 3, here you have 4, here you have 3, here you have 3. But for our purpose, it's more convenient to rotate the young diagram, and the columns are the numbers of cars in each pile. For example, you have 4, 3, 3, and you have 4, you have 3, you have 3. And also, every move consists of removing the bottom row of the solitaire and making a new column. Of course, if the new column is shorter than the previous, then this part is moved here to have this one. And this is a typical example of discrete dynamical system. You have the set of all partitions and an operator which in a period of time changes the state of the system, starting from a partition lambda to a new stage. This is the partition which is the image under the operator. So the operator, this is the updating functions of the system. And the main problem is starting from the initial stage to determine the stage when the system has two repeating parts. And of course, since we have a finite number of states, in some moment, the game finishes. Of course, you can make this as a graph. You have here the partitions, and with arrows, with oriented edges, you go from each partition to the next partition. You see that in this case, when you have 6 partitions of 6, you have a cycle here, which consists of 1 element. And when you have 7, the cycle is longer. This is the cycle. And the theorem is that when the total number is a triangular number, the number of the cards, then the Bulgarian Solitaire will converge into piles of size 1, 2, 3K. We should, I'll give you some idea about the proof of this theorem. And this is close to the solution of Tom, which was originally in 1981, but in the spirit of the exposition of Brandt, which was a little bit later, and we use the brilliant visualization of the Bulgarian Solitaire, the cradle model suggested by Andreas Björner. So also there are some other attempts. For example, there is an induction proof by Mestrovich, and also there are suggestions for concrete case to use spreadsheets, which are used in the financial departments when they described the incomes and the out and the many days in the debit and for everything. And what is the idea? So you have a partition. This partition, you take the columns here of the Young diagram, they are the number of the cards in each pile, and you rotate this in 45 degrees in order to have this configuration. For example, you have 4, 3, 3, you have here 4, you have 3, you have 3. And the next step, you think that the boxes are material points of the same mass, and you consider the potential energy of the system. the potential energy of the system. This is the mass time the acceleration, g, and also the height of the center of the box with coordinates ij. Of course, we can think that this integer is proportional to I plus j. And of course, the first move, you take these violet boxes and you move them here. You see that in the result of this, the potential energy of the system is the same. So and when you have here a box, several boxes above, the acceleration, the gravity put them below, and as a result, the potential energy falls. But in some moment, the potential energy will stop because decreasing because you have a finite number of possibilities. And it turns out that in the case of triangular number, this is the position which is stable. So this is combinatoric, easy combinatoric. You can see this in my paper if you're interested in details. And in the general case, it turns out that the potential energy is in the following way. For example, here, this is a partition of 7, or partitions of 7. You have a cycle, and this cycle corresponds to the following. In this case, all here, these boxes are filled with cards, and here you have a line with several more boxes. And it turns out that they move in this way cyclic. And of course, you can see that this thing is the same as if you have a necklace of this kind. Here you have 2 boxes, and you have 2 black things. The empty things, there are 3. Here there are also 3 empty positions. And of course, there is a formula which gives the number of the cycles which are in the end, depending on the number of the cards. And of course, you can ask what is the longest part for triangular numbers, because you have a graph, for example, here. You have a graph here, and you have a path. For example, here you have 1, 2, 3, 4, 5, 6. This is the longest path before you have a cycle. And you can ask about this one. And there was a conjecture about this, that for some partition, the longest path is starting from somewhere to reach this stable position. And Tom showed that starting from this partition, you get the longest path to be of this size, k times k minus 1. And not check this for the first 5 cases. And also he asked his students to write a computer program to check this till 10, and conjectured that this is the case for any case. It was proved in the 80s. And also there was some interesting observations about some reflections which are preserved, etc., etc. And the general case also was studied in the early 90s. But you can ask, how specific is this graph with the partitions, the oriented graph which is there? And of course, we know that the number of all partitions, this is the famous result by Hardy and Ramanujan. A little bit later, it was obtained independently by Uspensky, that the number of all partitions, this is this number here. And if you have the set of all labeled trees with n vertices, Cayley has this, that the number of this is n in power n minus 2, where n is the number of the vertices in the tree. And also, if you consider in the triangular case, the graph is that you have a labeled tree which is oriented, and you have a root which is the partition which corresponds to the triangle numbers. And if you remove the loop, you get simply a tree. And there is a theorem about the longest path, that the longest path is close to twice n, the number of all when you have the partitions. From the other side, there is a paper by Reini and Sekeresh, which gives that if you choose a tree by random of the set of all elements, all trees with n vertices with uniform probability distribution, then the expectation value is somewhere about square root of the number of the vertices in the tree. So if you apply in your case, you get that this tree, which corresponds to the partitions of n when n is a triangular number, this consists of many branches, but they are of small length. So the tree is with many branches, but it's not very high, because it turns out that this is the case. And of course, you know that in cellular automata, you have a configuration which is called Garden of Eden. So this is a configuration that cannot appear after one-time step. So this means that this is configurations without predecessors. Of course, the terminology comes from the fundamental paper by Moore, and by analogy of the concept of Garden of Eden, which in the Semitic religions was created of nowhere. And of course, you cannot enter there, you can only get out. And Hopkins, along with co-authors in a series of papers, they studied the Garden of Eden partitions in the Bulgarian Solitaire. There are also some interesting results there. In my talk, I don't give many results. I simply give, if somebody is interested in some branch of this, you can see the paper and read details. So, for example, here, these are the situations which are Garden of Eden in the case of 6 or the case of 7. And also, you can ask about the matrices related to this one. For example, with any graph, you have two matrices. One of them is the denseness matrix with rows labeled by edges and columns labeled by vertices. And you have the adjacency matrix with rows and columns labeled by vertices, and with entries 1 when you have an edge, a 0 if you have no edge. And this matrix, it has such a remarkable property that if you take the n power, the ij entry of the matrix, this is equal to the number of the paths of length m from the j to ith vertex. And if the graph is non-oriented, then the matrix, the adjacency matrix is symmetric, and also it's similar to diagonal matrix with 0 diagonal, and it is studied very well. So, but what happens in the case of the partitions? So, for example, what is the normal form of the matrix? You have such a remarkable property that in each column of the matrix, you have only 1, 1, and the other elements are 0. So, for example, here, this is the graph for 5. This is the matrix. In each column, you have only 1, 1, and many zeros. And again, you can translate this. There is a paper which consider this problem. This paper was related with the Collatz conjecture, 3n plus 1 conjecture, which states that if you have an odd number, the image of this odd number is 3n plus 1. If the number is even, you divide by 2. And the conjecture states that from each number, in several steps, you get 1. And of course, this is a very dangerous problem. When it was stated in Harvard, it destroyed the work for a month there, because all the people, they tried to solve this one. And Terence Tao recently, he posted a preprint. The latest version, this is in September a year ago, and he proved that for almost all positive integers, in the sense of logarithmic density, the minimal element of the orbit, this satisfies some inequality. And also for almost all k, you have some inequality for the minimal element in the cycle. For example, in this case, the graph consists of a tree which is planted on a circle for 5, for 7. You have several trees which are planted on the same circle, and it's easy to determine the Jordan normal form. You see, if you have a tree with a circle here, this circle corresponds to diagonal matrix with the roots of 1 here. For example, you have a circle of 3, you have 1 epsilon square, when epsilon, this is a primitive root of 3. You remove this circle and you look for the longest path. This is the longest path. To this longer path, you have this is of length 3. You have a block of 3, 3 by 3 with 0 on diagonal. So this is a Jordan cell. You remove this block and you do the same for the next one. So you have here only 1. This is this one. And you have something similar in the general case. But also, now I want to say something about the real life interpretations of the Bulgarian Solitaire. It has such a translation. You have a company which consists of a number of departments, and they decided to create a new department without hiring new people. So they take a person from each department and move this person to the new department. So if the number of cards of the powers is equal to the number of persons in the departments, the Bulgarian Solitaire, this is the greediest case when the new department is formed by taking a person from each department of the company. For example, here you have 3 departments. You take 1 person from each department, you form a new department. And also there are some generalizations. For example, there are Austrian Seminar, Carolina Seminar, Montreal Solitaire, Red-Green Bulgarian Solitaire, 3-dimensional, multiplayer, with several players sitting around a circular table, dual solitaire, random Bulgarian Solitaire of Popov, stochastic Bulgarian Solitaires by Timo Eriksson, Markus Jonsson. Mark Jonsson here is in the public, I think, and Jonas Sjöstrand. Generalized Bulgarian Solitaire by them again. This was quite recently, 2020. I simply want to mention, to discuss a little bit, the Austrian Solitaire. This is that a company has several machines, and each machine has, when new, a life of exactly L years. Each year, for each machine, the company deposits some money in the costs in the bank as a sinking fund. Then it buys as many new machines as it can afford, and the remaining funds are left in the bank until next year. So this is, you can translate this in the language of solitaires again. There was a dual Bulgarian Solitaire when you take the largest pile and you distribute it among the other piles. For example, here you have the largest pile is with 4. You take this 4, you add 1 here. The next step, when you have here 6, you distribute again and you form new piles with 1 card here. And also you have such an economical interpretation that in the regular Bulgarian Solitaire, the government takes the same money from each citizen and from each company, and then collects the same taxes from each person and each company, independently of how much is the income, and used the collect money to make a new company. In the dual game, this is something like Robin Hood, taking from the rich and giving to the poor. And it can be shown that if Robin Hood continues to take from the rich and to give to the poor, then the distribution of the fortune in the community become close to triangular. So the reason is that in this model, the cradle model, the dual Bulgarian Solitaire is equivalent to the regular solitaire, but it is obtained by transposition. For example, here this transport to this one, and also, so this is a geometrical proof that they are equivalent. And also it turns out that there is an old African game of Wari, which consists of cyclic order pits, which are filled with pebbles. And it turns out that the game is the same as the dual Bulgarian Solitaire. And I want to finish that the people from my generation, especially those from East Europe, they remember Mircea Crișan. He was the Romanian actor, and his Cucumber. So it was in Romanian, it was in German, it was in Bulgarian. In Bulgarian, there was also plates to play it with a gramophone. And the idea was that the student is preparing for an examination, and he tries from each topic to reach the cucumber, which blah, 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 and contains 98% of water. When they ask about the Suez Canal, it was saying the Suez Canal, blah, 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 blah. And something else to say about the Suez Canal? Yes, it contains 98% of water. So the Bulgarian Solitaire, this is in the opposite direction. You start from the Bulgarian Solitaire, and you can see that you can reach almost all parts of mathematics if you want to involve something, to do something similar. So this should be the anti-cucumber of Mircea Crișan. And finally, what is my contribution? When you go give a talk, usually we say I, we, etc., etc. So my contribution is that I'm almost sure that I taught the Bulgarian Solitaire to Gerd Almquist in 1998. I connected Henrik Eriksson with Borislav Buyanov 25 years later. I wrote the paper about the Bulgarian Solitaire in 2015, and all the time I'm trying to popularize the Bulgarian Solitaire. And what is the acknowledgement of my offer? If you see ResearchNet, it's updated once weekly. This week, it turns out that the total number of reads of my paper are more than 1,000. The paper inspired a short movie posted in YouTube. And finally, I received the following letter from Henrik. So it was, in Cyrillics here was something about that highly estimated professor and member of the Bulgarian and Academy of Science, etc., or rather Vesselin. I cannot thank you enough for your wonderful paper on the Bulgarian Solitaire. It's exciting, well written, illustrated, incredibly well researched, and generous as concerns the involvement of me and my circle, my best friend Gert, my advisor Björner, my son Kimo, my nephew Jonas, and my protege Anton and Emil. They are secondary school students. Your paper also freed me of my bad conscience for not writing up the story 10 years ago. So it was. And also, why I wrote this paper, maybe it's also asked me when I wrote it. In 2015, I was invited to present a talk for the spring conference of the Bulgarian mathematicians. The audience here is very mixed. There are researchers, there are people doing computer science, there are teachers, etc. And I had to find something which is good for everyone. So it was the case. Okay, thank you.
Okay, let's thank Professor Drensky for what was a very entertaining talk full of fascinating history. Are there questions? Comments?
Well, I'm not sure that they, can you hear me? I'm not sure about it. Yeah, so I'm very grateful to Vesselin, yeah. And also I want to say that I used my position in Quant to publish this problem which Sergey invented independently. And yeah, I was at that time the chair of math department in Quant. So that's how it's appeared, yeah. And Tom was really a brilliant guy. He was winner of many Olympiads and a schoolboy, and then yeah, he grew up a wonderful mathematician. So thank you very much. It was extremely interesting. It's really fantastically researched.
Yeah. Okay, thank you.
Thank you. More questions? More comments? Okay. If there are none, then may we thank the speaker again?
I want to ask one question. You have made generalization of this game, but do you have generalization when the player have a choice of the move?
Okay, you should ask Marcus about this, because what means the choice? Such you have the probability to take a card. For example, the statistics solitaire of Popov. Popov, he's a Russian mathematician in Brazil. In his case, you choose a card from a pile with some probability. For example, you have probability 1 second, a half from each pile. In the Swedish stochastic solitaire, you have the probability to choose each part, each card. So probably you can do this in the same way. You can choose a card or you can not choose a card depending on your desire. So here, there are so many generalizations that I'm not sure that maybe this is already done, but you should check.
Yes, because in this way, mathematical problem is very interesting, but for the player is maybe not so interesting because he have no choice. Actually, I don't.
Okay.
More questions? Or comments?
Okay, you can stop recording. I think to have a chat after this.
I'll stop recording now. Thank you again, Professor Drensky. We can continue the discussion in our native languages